Hi everyone, this tutorial is a continuation for the modeling of electrostatic levitation. A link to part 1 is given in the description. As I mentioned in part 1, the levitation process is unstable, so a feedback loop is needed to keep the sphere at a desired position. I will show you how to use a PID controller in Comsol for this purpose. I will start from the same file that I created in the last video. Insert a time domain study. I'll come back to the settings in this study later. So we need to make a few changes here. In the geometry, I will change the starting position of the sphere. So Z is 1.5. That's the position of the center of the sphere. And then under definitions, go to variables. And I will define a variable for the acceleration. You could use a solid mechanics physics interface to calculate the position of the sphere. But I will show you an alternative method to do it using global equations without adding any other physics interfaces. So the acceleration is F minus W divided by the mass. And then you can go to the electrostatics physics, disable the global equations that we used to find the voltage because it is no longer needed. Insert another node for global equations. And here we will define the velocity. So the velocity is the time integral of the acceleration, but we cannot define a time integral in Comsol. So alternatively, we can calculate the velocity by specifying the acceleration and the derivative of velocity. So the d operator is for the derivative. And we know that the derivative of v with respect to time should equal to the acceleration. So in this expression, v is the unknown which we need to find. The derivative of v is equal to acceleration, and acceleration is already defined. We need to change the units. So for the velocity, it's meters per second. And for acceleration, it's meter per second square. Okay, so the inconsistent unit message has disappeared now. As for the initial values, we know that the velocity is initially equal to 0. As for the acceleration, the initial value is equal to a. And then you can duplicate this global equations node. And now we will define a variable for the change in displacement. Let's define it by w, and this time we know that the time derivative of w is equal to velocity. The units should be updated. So it's meters and meters per second. So the initial value for velocity is 0. And for displacement, you can put any value here. You can take the value as 1.5 millimeters, but this value is not important, so I will just leave it. We care about the change in displacement. And now under definitions, we need to insert a moving mesh. So go to moving mesh, select prescribed deformation, select the sphere, and the prescribed deformation will be given by the variable w. And the remainder of the domain will deform freely, so insert deforming domain. And the boundary of the sphere should also move with the sphere. So insert prescribed mesh displacement. Displacement is also given by W, and then select the curved edges of the sphere. Finally, for the moving mesh, right-click and select a symmetry condition and select the symmetry axis. So that's all we need for the moving mesh. And before I show you how to define the PID controller, we need to define a global variable which will serve as the output variable of the feedback loop. So under definitions, go to non-local couplings and select average, select the sphere. Then right-click again on definitions, go to probes, and select global variable probe. So we need to monitor the position of the center of the sphere. And this position is given by the average of the z component of the sphere. So z is already a defined parameter in Comsol. It is basically just the position of the sphere along the z-axis. So we need to monitor this variable, and we want the sphere to stay at the height of 5 millimeters. The center of the sphere should be at 5 millimeters. So the goal for us is to use a PID controller to keep the value of this variable as 5 millimeters. And now to insert a PID controller, you need to go to the Developer tab, click on Add-in Libraries, expand Comsol Multiphysics, and you will find an option for PID controller, so just tick on it. In my case, it is already ticked. This feature is only available in Comsol version 5.5 and later versions. Once you have selected it, go again to the Developer tab, and from Add-ins, you will see PID controller, so click on it. So it is loading right now. Okay, so you can see that the general expression for the PID controller. C set is the desired position or variable that we need to get. Kp is the proportional gain constant. Ki is for the integral gain, and Kd, if I scroll down, Kd is for the derivative gain. So in this video, I will use only a proportional gain and derivative gain. So I will keep Ki as 0. The output from this PID controller will serve as the input, the voltage input at the top plate. So the voltage applied at the top plate will vary, and it will be controlled by this controller to help us get the desired position of the sphere. So the U-bias field, we will use the state variable that we found in the last video. This is the voltage needed to keep the sphere at the center. And you need to insert all the units. For Kp, I will use a value of 800. And the unit is volts per millimeters. The gain is 0. And the derivative gain, I will use a value of 10. So you need to make sure that all the units are consistent. The reference value or the desired position is 5 millimeters. As for the lower and upper limit, it's not really important. Just make sure it's a very low value and a very high value to avoid it from interfering with the PID controller. I will use 20 thousandths here. Uncheck the integral anti-windup and uncheck the filtering of the derivative. And now all the settings for the PID controller are complete. For the probe, you can see that Comsol has automatically defined the global variable, which we have defined. And then you need to create, click on Create. You will get a message from Comsol saying that a new physics interface has been created. This is in component 2. So Comsol created a global ODE interface, and it has defined the controller variable by this name. So UN control. So you need to copy this variable, go back to the electrostatics physics interface. And now for the input, instead of using V0, we will use the input. The input will be taken from the controller. And since this is taken from component 2, you need to insert a comp2 base name. So this is the input. And everything else is the same in the physics. The mesh is also the same. Now we will change a few settings in the time-dependent study. First, click on Show Default Solver. Make sure that the direct solver is chosen. Under Fully Coupled, go to Method and Termination and select Automatic Newton. This will help with convergence. And for the output time, we will save the solution from 0 seconds to 1.5 seconds in steps of 0.01 seconds. Go to time-dependent solver, right-click, and insert automatic remeshing. Since we are dealing with a moving mesh, when the mesh becomes severely distorted, the solver needs to remesh the geometry. So the condition type for remeshing, I will choose distortion. I'll keep the value of 2. So when the maximum distortion of any element exceeds a value of 2, then the solver will stop. It will update the mesh and then continue solving. So that's all. I will click on Compute now. Since this is a 2D simulation, the computation should be relatively very fast. And you can see Comsol has automatically generated a plot for the global variable that we defined. And it is showing how the position of the sphere is varying over time. So you can see in the beginning, we start from 1.5, and then it goes up. It overshoots the desired position, and then it is brought back to the desired position. So the oscillations decay very quickly, which is what we want. And this is what we can get from the PID controller. Okay, so the solution has been completed now. To plot the mesh, insert a 2D plot. Under Dataset, select the remeshed solution. Right-click and insert mesh. You can generate an animation by inserting a player. Okay, select all the frames. All right, so now we can compare how the position of the sphere varies relative to what I've shown you at the beginning of this video. So in this video, you can see that the oscillations decay very slowly. I purposely did that because I did not select a proper value for the derivative gain. So you can see that the sphere keeps oscillating for a very long time. And in real applications, this is very undesirable. Alternatively, with the proper value of derivative gain chosen, you can see how the oscillations die out very quickly. So it overshoots, and then within a half a second, it reaches to the desired position, and you can barely see any oscillations here. And the steady state error, as you can see in this graph, is 0. So it's exactly at the position of 5 millimeters, and that's why I did not use any integral gain. If the steady state error is not 0, then you will need to use an integral gain to reduce it to 0. So that's all for using the PID controller in Comsol, and this was also an application for a moving mesh. Thank you everyone for watching this tutorial.